Hello again, everyone. I hope you're doing well and that you were able to see the video lesson that I posted for you yesterday. Just wanted to talk about, just kind of briefly outline the remainder of this week. So today I'm going to provide you with a new lesson, go over yesterday's problems. Again, you can pause, skip through the video, and go about doing these problems, checking, correcting them at your own pace. So you will have a new assignment today. However, for tomorrow, I'm not going to be posting a video lesson. I want to give you guys time to get caught up so you can continue to work on Monday and today's assignment tomorrow. The quiz I mentioned, I'm going to make it obviously an at-home quiz. I will be posting it tomorrow. You will have till Friday to get it back to me. So I will be doing that obviously through Google Classroom as well. You could take a picture of your work and just post it back or upload it through Google Classroom through the assignment. Tomorrow's assignment 2 I will have posted up there as well. It's right here, but I'll post it again. One problem out of the AP problems, free response question, page 11, number 6. No graphing calculator. Allow yourself 15 minutes to work on this. We will go over it sometime during the end of the week. And then from the book, page 338, number 12. We're going to skip section 6.3 for now. It's usually a section I cover after the AP exam, and no, I have no further information if anything is being changed with that. So Thursday we're going to skip to section 6.4, which is exponential growth and decay, and then on Friday kind of wrap chapter 6 up with modeling population. But we'll definitely, into next week, have some review problems as well. I'll let you know what I'm going to do about how I'm going to give you a test. So I'll just keep you posted with that. So here are the answers to yesterday's assignment from the book and AP problems. So again, pause if you wish to redo these problems right now and see if you came up with the answers if you didn't get them the first time. If not, I'm going to go ahead and talk about the AP problems first, just like I did yesterday. All right, so looking at number 1, again, the answer here was E. We are asked if y is equal to sine of 3x, and just find the first derivative here. So if y is equal to sine of 3x, dy over dx, which is the same as y prime. We have to use a chain rule here, so the derivative of sine is cosine of 3x. Then take the derivative of the inside part here, so we are getting 3 cosine of 3x, which is E. So hopefully everybody was able to get that. Number 2, you could use substitution here is what we've been working on. So I'm going to go ahead and let u equal 3x plus 1. Then du over dx will just equal 3. And du over 3 is equal to dx. So then just rewriting this now, becomes the integral of u to the 5th times du over 3. We could say this is 1/3 the integral u to the 5th du. So we get 1/3. Since it's just one term here, this will become times u to the 6th over 6, again plus c because it's an indefinite integral. We can now replace the u with the quantity 3x plus 1. So we get that quantity to the 6th over 18 plus c, giving us a. All right, for number 8, just to write this a little better, integral of x squared cosine x cubed dx. Again, we can use u substitution. I'm going to let u equal just x cubed. That way, when I go to take the derivative of it, this will become 3x squared, and it's this x squared that will divide out with the x squared that's in the integral problem. So now du over 3x squared equals dx, and replacing this now, we will get the integral of x squared cosine u times du over 3x squared. Again, this is where the x squares divide out. I'll put the 1/3 on the outside, the integral of cosine u du. Keep the 1/3 here. Now, always be careful with this part. The antiderivative of cosine u will become sine u, because think again, derivative of sine will give us cosine. So then this becomes sine u and then plus c, and then we'll just go ahead and replace u with the x cubed. So we get 1/3 sine of x cubed plus c, giving us b. All right, for number 9, we're asked to find f prime of 0 if f of x is equal to the natural log of all of this. So just to write that a little clearer, it's the natural log of x plus 4 plus e to the negative 3x. So first finding f prime of x, if this is a natural log of this entire expression, it becomes 1 over this entire expression times the derivative of, again, the inside stuff. So we're going to get a 1 plus 0 here when we take the derivative of 4. And then this will become e to the negative third times negative 3. So I'm just going to write it as 1 minus 3e to the negative 3x. And now we want to find f prime of 0. So we get 1 over x just becomes 0. So we get 4 plus, this becomes e to the 0, which is 1, times 1 minus 3. Again, this part here will just become a 1. So up top we'll get a negative 2 and 5 in our denominator. So A for number 9. All right, for 16, if the line tangent to the graph of the function f at the point 1, 7, so this is where the line is tangent to our curve, and then our tangent line also passes through this. So just looking at a generic curve here, and we have a tangent line. So if it's passing through a point here, and I just drew this real quick, so this is just 1, 7, and then let's say this other point down here is going to be the point negative 2, negative 2. Finding the slope of this tangent line is just the slope formula, the y2 minus y1 over x2 minus x1, so that's all we really need to do, because f prime of 1 is right here. That is our derivative, or the slope of our tangent line at x equals 1. So here we will be looking at that f prime of 1 is going to equal negative 2 minus 7 over negative 2 minus 1, giving us negative 9 over negative 3, which is 3. So that's giving us C. All right, now let's take a look at the problems from the book. Now again, you didn't have to use this alternative method for every single problem, but maybe try it sometimes. And I'll give you a hint, number 34, it works out a little nicer, just like the last example I showed you in yesterday's video. So let's go ahead and take a look at 33, where we have the integral from negative pi over 4 to 0, tangent x, secant square x. Now I'm going to go ahead and do all of these using this alternative way, but again, I just wanted you to try it at least once. So here I'm going to let u equal tangent x, because again, when I take the derivative, I'm going to get that secant square x, which will divide out with the secant square x in the problem. So du over secant square x equals dx. I'm also going to write over here that when x equals negative pi over 4, u is equal to tangent of negative pi over 4, which is negative 1. And then when x equals 0, u equals tangent of 0, which is also 0. So now this becomes, I'm going to just write it out once here, that u equals negative 1 to 0 of u, because that's what I let tangent x equal, secant square x times du over secant square x. Again, secant square x is divide out. Now I have the integral, again, u equals negative 1 to 0 of u du. Taking the antiderivative here, I get u squared over 2 from u equals negative 1 to u equals 0. I'm going to just go across here with this. And at this point, I don't have to bring back in the tangent x. I just start with the 0. So 0 squared over 2 is just 0, minus negative 1 squared is positive 1. So this is giving me that negative 1/2. So again, this different method could be a little bit of a time saver. Right, let's go ahead and take a look at 34. Integral from -1 to 1 of 5r over 4 plus r squared squared dr. U substitution, I'm going to go ahead and let u equal to 4 plus r squared. Because when I take the derivative of this, I'm going to end up with just a linear r, which will divide out with the linear r in the numerator. So du over dr is going to equal 2r. So du over 2r equals dr. When r equals -1, u is going to equal 4 plus -1 squared, which is 1, so it's going to give us 5. And when r equals +1, u also equals 5. So that's a good thing, seeing this right here. Hopefully you should know what the answer, even if you looked at it, but knowing that these two are the same, we have a nice quick problem here. So just rewriting this now, this becomes the integral from u equals 5 to u equals 5 of 5r over u squared times du over 2r. We really don't have to do anything else because of the limits of integration. Since they're the same, we just know our answer is now 0. Okay, looking at 35. Integral 0 to 1, 10 radical theta over 1 plus theta to the 3/2 squared d theta. Let's let u equal this 1 plus theta to the 3/2. du over d theta becomes 3/2 theta to the 1/2. 3/2 minus 1. So then du, I'm actually going to multiply by the reciprocal here, so we'll say 2/3 du over square root of theta, just dividing by this, equals d theta. And then finding the new limits here when theta equals 0. Substituting this in here, this is just going to give us 1, u equals 1, because 0 to the 3/2 is 0. And then when theta equals 1, 1 to the 3/2 is 1, so u is going to equal 2. So now this becomes the integral from u equals 1 to u equals 2 of 10 radical theta over u squared times 2/3 times du over 3 radical theta. Oh, no, I shouldn't have that 3 there. I already had it up there. Okay, so now we can see that the radical thetas do cross out. I'm actually going to take this 10 times 2, giving me 20/3, pull that to the outside. Still have the 1 to the 2. Remember, those are the values for u. I'm going to write this as u to the -2nd du. So we get 20/3 times u to the -1st over -1. And then that's from u equals 1 to u equals 2. Again, I'll just go across here. So we're going to have 20/3. Just to rewrite this, -1 over u from 1 to 2. So we get 20/3. This will become a -1/2 minus a -1. So this is really just 1/2. So we get 20/3 times 1/2, which is 10/3. Alright, and then we have one more problem from here, number 37. Integral 0 to 1, square root of t to the 5th plus 2t times the quantity 5t to the 4th plus 2 dt. Alright, so what can we let u equal here? Usually, if it's something under a radical, we want that or it's the part with the larger degree, because when we go to take the derivative of t to the fourth, we're going to end up with 5, or t to the fifth, we're going to end up with 5t to the fourth, and that's exactly what we have over here. So I'm going to let u equal t to the fifth plus 2t. Then du over dt equals 5t to the fourth plus 2. It matches this quantity perfectly, so we know we did that correctly. So then du over 5t to the fourth plus 2 equals dt. When t equals 0, u is going to equal 0, because again it's t to the fifth plus 2t, so that doesn't change. But when t is 1, u is going to equal 1 plus 2, giving us 3. So now this becomes the integral from u equals 0 to 3 of the square root of u times 5t to the fourth plus 2 times du over 5t to the fourth plus 2. So these quantities divide out. I'm left with the integral 0 to 3 u to the 1/2 du. So this becomes u to the 3/2 over 3/2. Again, from 0 to 3, keeping in mind these are both the u values here. So this will become the reciprocal 2/3. I'll just keep this on the outside. And then we'll have, I'm going to combine this one step. So we're going to get 3 to the 3/2 minus 0 to the 3/2. So this becomes 2/3 times, really this is the square root of 3 cubed. So this becomes 2, and then this will become 3 radical 3 over 3. These 3's divide out, so we just have 2 radical 3. Alright, so again, if you weren't able to come up with these, please try them again. Email me with any questions. Alright, we're still in section 6.2. This is a big section with multiple ways to find different integrals. Just remember back when we were taking derivatives, how many different rules we had: the chain rule, product rule, quotient rule. So this is the integral way of trying to apply those when we can't just use the power rule. Alright, so this next part is called separation of variables. It's a different way to solve differential equations, and it is used or found a lot on the AP exam, some multiple choice questions, but there's also some free response non-calculator problems as well that have you go through this process. So let's take a look at what this involves. Alright, so our first example, we're given our first derivative is going to involve x's and y's. So if you remember, if we wanted to find the derivative of this, we had to use implicit differentiation. Well, to go backwards, this is the approach that we want to use. So instead of showing y prime here, I want to write it as dy over dx. And we have to get a little fancy with the way we're going to approach this. This is why we need to really know our algebra skills here. So in order to separate the variables, I need to factor. And the way I'm going to factor here is by grouping, because my goal is to solve for y in terms of x. So right here, I want to factor by grouping. And I'll review that. Okay, so with factor by grouping, I want to get my x terms together, so I'm going to rewrite this. I want to see what's in common. There's nothing in common of these first two terms here, which actually I rewrote that wrong here, so let me adjust this, and then we should be okay. 2x squared y. So now if I look at my first two terms, I do have an x squared here. So I just want to factor out what these two terms have in common, which is the x squared. It's going to leave me with a 2y minus 1. Then I want to look at these two terms. I'm going to factor out a positive 3. And then what's left over is a 2y minus 1. So the 2y minus 1s are what we call a common binomial factor, and we're going to factor that out. And then what we have left is the x squared plus 3. So if you notice, in each set of parentheses, we just have a single y or just an x. We don't have a combination of x's and y's. So this is where we separate the variables. I'm just going to abbreviate it as SOV. I'm going to bring the 2y minus 1 to the other side by dividing, so this becomes dy over 2y minus 1. I'm going to multiply the dx to the other side, so we have x squared plus 3 dx. Now these problems are rather long. We're only doing 2 examples here, but it is very necessary. Okay, so next what I want to do is integrate both sides. So the way I'm going to write this, the integral, I'm going to write this as 1 over 2y minus 1 dy is equal to the integral of x squared plus 3 dx. So because this is 1 over something, we could use u substitution, which I am going to actually do, just to take away the guesswork. So I'm just working on the left side here. We don't need it for the right side. So I'm going to let u equal 2y minus 1, then du over dy equals 2, and du over 2 equals dy. So this will become the integral of 1 over u. I'm just going to put the 1/2 out in front, and then du, and the rest stays the same. So now this will become 1/2, and then looking at 1 over u, we'll have the natural log of the absolute value of u. I'm going to put the constant here because these are both indefinite, but I'm going to label it c sub 1. On the other side, we will get an x cubed over 3 plus 3x plus a different constant. We'll call it c2. In the end, all of our constants combine anyway, so we'll just call it a c in our final step. My goal here now is, because I want to solve for y, I'm going to replace the u again with the 2y minus 1. So we get 1/2 times the natural log of the absolute value of 2y minus 1. And at this step, I'm just going to bring the constant over. So we're going to get 1/3 x cubed plus 3x plus a different constant. I still might not be done with this. I'm going to call it c sub 3. Next, I want to multiply both sides by 2, so this will give me the natural log of the absolute value of 2y minus 1. I'm going to double everything over here, so we're going to get 2/3 x cubed plus 6x. I think this should be my final constant here, so I could call this just c. Now, if we were to stop here, which, I mean, the problem has been long enough, this would be called the implicit solution, because we are not specifically solved for y in terms of x. So this is the implicit solution. We're going to continue this, though, to find the explicit solution. So I'm going to continue this on the next page and just rewrite this part. All right, so this adds a few more steps. We're going to use a base e for each side. So what's going to happen here, e raised to the natural log of anything is just this anything, so still keep absolute value of 2y minus 1. Over here, though, I'm trying to pull out a constant, so I'm going to use a property of logs, or exponents rather, to keep the 2/3 x cubed plus 6x here. Then it's going to be times e to the c, because if we think of this backwards, if we have the same bases, we write the base once and we add the exponents when we're multiplying powers. So now this e to the c, I'm no longer going to use a c, but this is still just a constant. I'm going to call it a. And if you guys recall back to a lot of the exponential, like investment problems, compounded interest, we have this amount, so it's usually a times e to the rt or kt. So this is where the a is going to come from. So now I have absolute value of 2y minus 1 is equal, put that a out in front, e to the 2/3 x cubed plus 6x. What makes this problem even longer is now we have to get rid of the absolute value, so we're going to separate this, because this could equal a positive value over here, or it could turn out to be the negative. So we're going to have 2y minus 1 is equal to a times e to all this as the exponent, or 2y minus 1 just equals the opposite of this. And then And finally, to get y by itself, we'll just add 1 and divide by 2 on both sides. So y is going to equal positive a to 2/3 x cubed plus 6x plus 1 all over 2. Make sure this plus 1 is not up here with the exponent. Or y equals negative a times e to 2/3 x cubed plus 6x plus 1 all over 2. So both of these are the explicit solutions. Now eventually we're going to be asked to find out what a is. At this point you would just use one or the other to find it. You don't have to use both, and we do want to keep them separate. We don't want to just say it's plus or minus and keeping it as 1. So we do want to show it separately, because eventually when we get into the other sections it will make a difference. Alright, let's try one more example. Alright, so this one is a little bit different. We can't factor by grouping like we did with the last problem. Each problem is going to present a slightly different approach. We have to be very clever. So how do you think we can separate these? Again, it's e raised to a sum of something. So pause the video and see if you can think of anything. The clue is what we did at the very end of the last problem. We can separate this using the laws of exponents. It becomes e to the 2x times e to the y. So if you were thinking that, nice job. Next, what we want to do is move the dx over to the right side, e to the y over to the left side. So I'm going to divide by e to the y, and then over here I'm going to multiply by dx. So next we're going to take the integral of each side. So again, at this step, this was the separation of variables. So I'm going to write this as the integral of e to the negative y dy, then the integral of e to the 2x dx. If we wanted to use u substitution, we'd have to use it twice. So if you did, you could call u equal to e to the negative y here, but then you could use a w over here. If, I'm sorry, e could equal just negative, or u could equal just negative y. But then over here, use like a w. Don't use u twice. Let's try this though without, because we know the derivative of e to the negative y is going to be e to the negative y times a negative 1. So to make that negative 1 go away, let's put a negative 1 in front, plus c1. Over here, the derivative of e to the 2x is just e to the 2x. I could use that for the antiderivative. Then I would also have for the derivative times 2, so I'm going to need a 1/2 out in front. So just double check. This should give us, when we take the derivative of this, we should be getting e to the 2x. Call that plus c2. I'm going to bring the constants all over to one side, so we get negative e to the negative y equals 1/2 e to the 2x. Call that plus c3. Then I want to divide everything by negative 1, so we get e to the negative y equals negative 1/2 e to the 2x. And I think we could just have plus our overall constant at this point. Also at this point, this is the implicit solution. So to get the explicit, we want to solve for y in terms of x. So I'm going to take the natural log of each side. Now, I want this to be positive, so I need the absolute values. So negative 1/2 e to the 2x plus c. Keep that in the absolute values. Again, the natural log of e to anything is just going to leave us with this anything, so we get a negative y equals the natural log of this quantity. And my last step is just to divide by negative 1. So y is going to equal the opposite of the natural log of this quantity. Not a very pretty answer, but it is the answer. It's the explicit solution. So there were 2 examples over using separation of variables. We'll continue to go over this. Tomorrow I still will have the answers posted to today's assignment, but again, continue to work on them. and let me know if you have any questions. Back into that page here. Alright, so here's the assignment. Pages 322, 323. These problems when you get to 45, just parts A and B, and then some more problems off of pages 72 and 73. Again, you can look at the next page and pause it if you don't have your book with you. Please let me know if you don't as well, or if you need any other copies made for you or any of the other problems. Alright, so give this a try. Again, let me know if you have any questions.